RL circuit. In the circuit shown in figure, epsilon is equal to 60 volts, R1 is 40 ohms, R2 is 25 ohms, inductance is 0.3 henries. Switch S is closed at t is equal to 0. Just after the switch is closed, part A, what is the potential difference VAB across the resistor R1? Okay, so the voltage across the inductor, VL, is related to the current that flows through the inductor. It's inductance L multiplied by di dt. And since the current through an inductor cannot change instantaneously, because if it changes instantaneously, you would have infinite voltage here, you will see that the current at t is equal to 0 minus must be equal to the current at t is equal to 0 plus. So I2 will be equal to 0 amperes. And V2, the voltage across this resistor R2, will also be equal to I2 times R2, which is 0 volts. Then this voltage epsilon will be appearing across R1 only, and it will not appear across R2 because R2 will have 0 voltage, and it will also appear across the inductor. So we will see that this voltage appears across R1. So this is the positive terminal, this is the negative terminal. So A is at a higher potential with respect to B, and V1 will be equal to VAB, which is epsilon. So VAB is epsilon, which is also equal to the which voltage, because there is no voltage drop here, it will also be equal to VCD. All right, so VAB will be equal to VCD. So the answer to part A, VAB, which is voltage across resistor 1, will be equal to the supply voltage, which is 60 volts. Part B, which point A or B is at a higher potential? Well, the voltage drop across R1 is in the direction of the current flow, so I1 must be flowing in this direction from A to B. That's the direction of the current. There is no current flowing through this branch, so at t is equal to 0 plus. Therefore, the voltage drop is from A towards B. So we will see that R1 voltage drop is in the direction of I1. So point A is at a higher potential compared to point B, because VAB is positive. So VAB is positive, greater than 0 volts. Part C, what is the potential difference VCD across the inductor L? Well, since there is no voltage drop across R2, VCD is simply equal to VAB. So we can say that since V2 is equal to 0 volts, we must have VAB equal to VCD, which is the supply voltage, 60 volts. So that's what we should have. Now, part D, which point C or D is at a higher potential? Well, VCD is positive. That means the point A and point C are at the same potential, and point D and point B are at the same potential. So C is at a higher potential. So point A and point C are at the same potential. No voltage drop across R2. At the same potential. And also point B and point D are at the same potential. And so we can see that point C is at a higher potential compared to point D. Part E. So let's see. After this, the switch is left closed a long time. So we close the switch and then opened. It's closed for a long time and then opened. Just after the switch is opened, what is the potential difference VAB across the resistor R1? Okay, so when the switch S is left closed for a long time, this implies that we reach steady state. There will be a steady state current flow so that the time derivative of the current will be equal to 0. di dt equals to 0, which means the voltage across the inductor, VL, will be equal to 0 volts because it's L di dt. And then, since there is no voltage drop across this inductor, the current I2 will be equal to epsilon divided by R2 at steady state. So at steady state, the current will be I2, which is just before the switch is reopened, epsilon divided by R2. So epsilon was 60 volts, R2 is 25 ohms, so it is 2.4 amperes. And when the switch is opened again, this I2, the steady state value of I2, must also flow through R1. So it's going to complete the circuit like this. So we can see that when the switch is opened, I2 must flow through R1, and I2 cannot change instantaneously. It's the current through an inductor. So what we have here is now this equivalent circuit, R2L. I2 flows through this circuit. Then we can calculate the voltage across R1, VAB. VAB, as you can see here, is equal to minus I2 R1. Because I2 flows in this direction, the voltage drop is from B to A now. So VAB is equal to minus 2.4 times 40 ohms, which means voltage across the resistor R1 will be minus 96 volts. So that was the question in part E. Which point, A or B, is at a higher potential? As we have noted here, since current flows from B to A, B must be at a higher potential. So since I2 flows from B to A, B now is at a higher potential in this situation. What is the potential difference VCD across the inductor L? Okay. So you can see here from this circuit, potential drop across R2 plus the potential drop across the inductor plus the potential drop across R1 must be equal to 0. So it is V2 plus VL plus V1 must be equal to 0. That's the Kirchhoff voltage law. So we can see that after the switch is opened, we must have V2 plus VL plus V1 is equal to 0 volts, Kirchhoff voltage law, and voltage across the inductor now will become minus V1 minus V2, which is minus 60 minus 96. So right after the switch is opened, the voltage across the inductor is minus 156 volts. Before it was opened, it was 0 volts because we reached steady state. But after it's opened, this is at steady state, after it's opened, the voltage across the inductor will be minus 156 volts. So V2 plus VL plus V1, where V1 is 96 volts. So we have therefore 60 volts appearing across this because the voltage was 0 at t is equal to 0 minus. So we have minus 60 minus 96 minus 156 volts. Which point, C or D, is at a higher potential? Now you can see that the voltage I have calculated across the inductor, so this was point C here, is negative, which means D is at a higher potential. So I have found that VCD is let's remember where point C was. Point C is here, so VCD is the voltage across the inductor. VCD is equal to VL, which is minus 156 volts. So we can see that D is at a higher potential. Okay, so let's see what we have done here. We close the switch. As soon as we close the switch, this battery is connected in parallel to R1. So the potential difference across R1 becomes 60 volts. That's this voltage supply. And current flows in this direction, which means A is at a higher potential. A is connected to positive terminal, B is to negative terminal. And what is the potential difference VCD across the inductor L? The current through the inductor cannot change instantaneously. Before the switch was closed, the current was 0. So that means this current through the resistance R2 will be equal to 0. So there will be no voltage drop across this. So VCD will be equal to VAB. So that's what we see here. It is 60 volts. And which point, C or D, is at a higher potential? Well, C is A, D is B. No voltage drop here, so C is at a higher potential compared to D. Now the switch is left closed for a long time, which means we reach steady state. When we reach steady state, L di dt becomes 0. The voltage drop across the inductor becomes 0. So this 60 volts appears across R2 and R1. And we can see that I2 will be equal to epsilon over R2, which is 2.4 amps. Now, because this current, 2.4 amps, cannot change instantaneously through the inductor, when the switch is reopened, this must be the current that flows in this circuit, so it will flow through R2, L, and R1. So we can see that VAB will be equal to minus I2 R1 minus 96 volts, and now B is at a higher potential compared to A. And what is the potential difference across the inductor? The potential difference across the inductor was 0 volts at steady state, but now we have this I2 flowing through this circuit, so we have VR2 plus VL plus VR1 equal to 0, which means VL is minus V1 minus V2, so we will have minus 60 minus 96 minus 156 volts. So this potential difference is 60 volts, and then this potential difference is 96 volts, and this potential difference is minus 156 volts. Okay, so that's the way I have defined here. This is V2, this is V1, and this is VL. So with this convention, plus minus, plus minus, plus minus. So what about the point C or D being at a higher potential? Well, point C now I have the way I have looked at this voltage VCD, it turned out to be negative, so that means D is at a higher potential now instead of C.